Let's take a look now at the final example here of this section, example number 5, dealing with one of these kind of awkwardly shaped tanks. This is very much going to be like our opening example. So suppose that liquid is draining from a conical tank that has a radius of 4 centimeters and a height of 16 centimeters. Okay, so right away off this first sentence, I'm going to notice that the thing that's going to be moving in this question is the liquid that's going to be in the tank. So I'm going to go ahead right away and I'm going to start to sketch out where the liquid might end up being in this tank, right? So maybe it's like up to this height and everything down below is going to be maybe water or something of that sort. Now I can also see that the tank itself is given some dimensions, and these dimensions are going to be fixed, so I'll draw them in black. I have 4 centimeters for this top radius, and then I also am going to end up with 16 centimeters for the overall height. And I should notice that even in the stopped picture, these dimensions are going to remain the same because, again, they aren't changing at all. It's the same tank. Now, suppose that the liquid is actually draining out at a constant rate of 2 cubic centimeters every minute. So again, I have to remember that the water here is like slowly going to be dripping out of this tank and forming, some sort of like a puddle over here on the ground. And so if I have the water then leaking out of this tank, that's changing the volume of the water. So I can say that the volume of the water in the tank is going to be given by dV dt, and since this volume is going down, I'm actually going to make this negative 2 because the volume is decreasing in the tank. That's where the negative comes from. So the question here is, at what rate is the depth of the liquid actually draining? Or what is the rate at which the depth of the liquid is changing at the instant when the liquid in the cone is 8 centimeters deep? So I should be able to see a couple other things here. If I was to imagine that there's kind of like a top circle of water that's sitting in here, then that circle of water obviously has some sort of height, right? It's some distance from the bottom. So I'll label that as h. And what I'm curious about apparently is what is dH dt, right? What here is actually changing? Or how quickly is that height changing more specifically? And then when I go to my stopped picture, I can see that I'm interested in stopping when the water that's in the tank is specifically going to be locked in at a height that is 8 centimeters. So I'm going to stop that right there. Okay, so I have to think here about how exactly I might be able to relate all of the different variables that I have ultimately here in my picture. What I can see is that I really only have 2 variables, right? I have a d, I have an h, I have and a v. But if I wanted to start to try to relate these variables, it might seem difficult to find a formula that only contains those 2 variables. It might be more kind of intuitive to start with an equation for the volume of the water in the cone. So 1/3 pi r squared h. But again, I should notice right away that there are going to be too many variables here. Right? There are going to be too many variables here to work with. And I can see this is going to be the case because if I was to take the derivative of this right away, I would know that in the derivative there would be a dr dt and a dH dt. And while I know that I'm looking for the value of dH dt, I'm not looking for the value of dr dt, and I'm not given the value of dr dt. And so I wouldn't be able to actually evaluate this derivative very easily. So our goal is instead going to be trying to replace one of the variables that we have here, specifically the variable of r, and put that in terms of the variable of h. We have too many variables right now, and we can't work with what the derivative of this would look like. So let's go ahead and start to think about how we could actually attempt to get rid of this variable of r. I'll even write that here, at least as our objective. We want to, I'll say here, rewrite that. I'll say we want to replace r in terms of h. So I want to get rid of that so that way the only variables in here are r's and h's. Now to do this in a cone, it's actually fairly simple. We can do this by highlighting a couple things that we might see down here in this picture below. So what I'm going to start by taking a look at is actually one other thing in this picture that I now know to be fixed. If the height here is locked in at 8 and the picture is no longer moving, I can definitely state here that the radius for the water is fixed. I don't know its value, but I know it's not moving anymore. So that's locked in. And if I can kind of see here, I've created a little red triangle. Specifically, it's a right triangle. But there's another right triangle that's also going to be able to be seen in this picture. And it's this green one that I'm sketching that kind of uses the full tank to create its outline. Now this is also going to be a right triangle, and both of these triangles contain this bottom angle. So that means that if they have this angle in common, they both have a right angle, and that means that these corner angles here have to be the same, and these are similar triangles. And if I have similar triangles, you might recall from like a geometry class that the sides of these triangles then should be in proportion. So I'll state here that by similar triangles, we know that I could say R, the radius of my small red triangle, should compare to the radius of the large triangle, which is 4. And that ratio should be identical to comparing the small height, which we would actually in this case just call h. Remember that for the moment, while in the stopped picture we have h working down here, we're still in step, or h is an 8 down here, we're still working in step 1, which means that we're really focusing on the way that the similar triangles would end up looking in our picture up here, where we just have kind of an arbitrary height of h. And now I could see that I could compare that height to the height of 16, which is the overall height of the tank. Now if I go ahead and I rewrite this, notice that if I multiply 4 over to the other side, I'm going to get 4h over 16, which is the same as h over 4. So I have now actually found a way to rewrite r in terms of h's. So we update our equation to be volume is equal to 1/3 pi h over 4, again going in place of r, should now be squared, times h. And in fact, I could write this down like a little bit more. I could simplify it further. Notice here that if I square the top and the bottom of this fraction, the denominator would be 16. If I combine that together with my 1/3, I'm going to get 1 over 48 pi, and then I'll have h squared times another h, and I'll have h cubed. So this would be now a good equation that I could use that only has v's and h's. Now I can move to step 2, where I'm going to go ahead and take the derivative of the left side and the derivative of the right side with respect to the variable of t. All right, on the left side, I know I'm going to just end up with dv dt. On this side, I can see that I'm going to have stuff to the 3rd power, so I'm going to bring the 3 down. When I take 3 over 48, that's going to simplify actually to 1/16, and then I'm going to have pi h squared, and then chain rule, derivative of the h, which would be dh dt. So now I can think about what's going to be happening in step 3 when I actually move to my stopped picture. So in here, I can realize that my dv dt is -2. I can see that my value of h in this picture right now is going to be 8, and dh dt is unknown, which is totally fine, because that's what I'm looking for. So let's see, if I simplify this up a little bit more, notice here I'm going to get 64 over 16. That's actually going to simplify to just 4. And so if I kind of take this all the rest of the way, I'm going to end up with dh dt is equal to -1 over 2 pi, because when I divide that 4 pi over, I'm going to get 2 and a pi in the denominator. Now, of course, I want to put some units on this. I can see here that I've been measuring time in this problem in minutes, and I've been measuring heights or lengths of things in this problem using the units of centimeters. So my height here is decreasing. That's indicated by the negative, which makes total sense because my height is going down as as the liquid drains out of the tank. And it's going down at 1 over 2 pi centimeters per minute. Again, please note that I am writing all my answers here again as exact values. I'm not writing decimal approximations, and you want to make sure that you do the same thing as well. Now, I do think that cone problems here, or cone tanks, are some of the most difficult questions here because they do require that we do this extra work here of working with similar triangles and taking a complicated formula and simplifying it down to a formula with less variables. If you happen to have any questions on problems like this, please by all means let me know. But the number one way to improve in this section and to make sure that you really understand what's going on is, of course, to take a look at the worksheets. The worksheets for this section have a lot of problems of differing types, and it's a really good way to make sure that you're going to be really prepared for the upcoming exam.